inclusive. Yeah, we continue where we, just as a brief reminder, accept. Okay, no, it works. So just a brief reminder what we've done yesterday and what the whole setup is about. So I've given you a lot of sort of graph theoretical, graph algorithms motivation for a very basic question in logic, namely the model checking problem for a given logic L on a class C of structures or graphs. So everything I talk about can be generalized to structures, but it doesn't really add any new insight. So I'll stick to graphs. So basically the problem is we fix a class C of graphs, and then as input we are given a graph from that class and a formula in our logic L. We want to decide whether that should be G here. The formula is 2 in the graph we are given. And we study this under the parameterized complexity model. So we declare the size of the formula as a parameter. And then the notion of the concept of tractability we are using is fixed parameter tractability, where we declare this model checking problem to be fixed parameter tractable if it can be solved in this time here. So there's some function in the length of the formula, which is typically bad, as Moshe pointed out yesterday, and then a fixed polynomial in the degree of the graph. So change this to A and everything's fine here. Yeah. And one other complexity class in parameterized complexity I want to mention, because we are proving lower bounds which are much stronger than FPT. This is the class XP, which basically is the type of problems you can solve in time, the size of the graph raised to some function of the formula, right? And this is basically the parameterized exponential time, because the parameter occurs in the exponent of the, and this is a super large class. And it's provably larger than FPT, and it's very large. And so for any reasonable sort of upper bound, we are interested in FPT, but later on I'll show you some lower bounds for XP. Okay? And yeah, so basically the program I set out, the question we want to study is, for the logics like first order logic, monadic second order logics and its different variations, can we somehow identify a structural property of graphs so that the model checking problem for this logic becomes fixed parameter tractable on C? Well, if and only if the class of graphs has a certain property P, right? And I've already mentioned probably we won't be able to get such a precise characterization. It will certainly have to be under some complexity theoretical assumptions, but I'd like to get as close to this as we can for the logics we like. Right? And so the hour yesterday was basically spent on proving upper bounds, and we've seen various tractability results. So first of all, we've seen some of these classes here you see in the diagram, and then I proved the Cosell's theorem, which has an MSO2, so well, again that should be 2 here, is FPT on the class of bounded tree width. Then there's some variation I didn't really talk about on bounded clique width graphs. And the last thing you saw was basically here for bounded degree graphs and bounded local tree width, where we can do first order model checking.
I don't mind to change those ends.
Yeah, I know. But it was a drinks reception, so I couldn't count up. No, I simply forgot to change them. So these are the results here, just as a quick recap. Cosell's theorem, which is that MSO2 is FPT on any class of graphs of bounded tree width. And then the last thing we saw was this locality-based method to prove that first order logic is fixed parameter tractable on graphs of bounded degree. And basically the method was you apply Guyffin's theorem to reduce the problem for first order model checking to checking these kind of local formulas here. And so basically all we had to do to find a first order model checking algorithm on a class of graphs is to be able to solve first order formulas in local neighborhoods around the vertex. So the whole approach is based on you take a vertex, you compute its R neighborhood, where the radius here just depends on the formula you want to model check, and then you decide whether a certain formula is true in here. And if you can do this, then basically the general technique we've seen yesterday would allow you to extend this result to first order model checking on the complete graphs. Right? And that was the basis for Frick and Groh's proof that FO is FPT on planar graphs and of graphs that are locally bounded tree width. So every neighborhood has a small tree width. So it took me a little longer yesterday than I anticipated to come this far. In fact, you asked a lot more questions there than I thought you would, which is good. Keep doing this, and I'll adjust. So 2 things I didn't mention, and I want to sort of hand wave over now, are sort of more recent results. So another thing that Flum and Grohe proved not so recently was that first-order model checking is also FPT on any class of graphs where you exclude a fixed minor. Yeah, and then we extended this, and I'll show you how this goes later on. So this is a theorem. I would like to sketch the proof idea now. Right. So C is a class of graphs now excluding a fixed minor, and let me tell you, I mean, Albert talked about this already, but sort of what is a minor? We say a graph H is a minor of a graph G if it's obtained from a subgraph of G by edge contractions. Yeah, so edge contraction means you take an edge in your graph and then you contract it into a single vertex. Yeah. You keep all the original neighbors, so these guys and these guys, but then you delete the self-loop basically you would get by contraction. Yeah. So that doesn't really tell you much how minors look like. So here's an alternative characterization that's equivalent. Well, I want to find this graph H as a minor in G, and so this is possible if and only if the following is true. So for every vertex in the graph H, let this be H here and this is G, I want to find a connected set of vertices in the graph G. So that vertex here corresponds to this set of vertices, and this one to that one, and so on. Right? And for every edge in the graph H, I want an edge that connects at least two vertices from the corresponding patches here, as we call them. Right? So here, this edge between that vertex and this vertex would correspond to this thing. And if you find this, then what you can just do is you contract all these gray areas into a single vertex, and what you get is just, and then you throw away everything else, and what you get is a minor of this, of H in G. Right? And so the union of these things, so the union of these edges and of the gray areas is called a minor map or model of H in G. Right? And we'll see this later on quite a lot. So in such classes of graphs, so I call C excludes a fixed minor if no member of C contains the graph H as a minor. And these type of graphs have been studied a lot in structural graph theory, and sort of the object that Robertson and Seymour studied in a sort of graph minor project. And it's in fact their work that provides all the ingredients we need. So what we want to show is now that on such classes of graphs excluding a fixed minor H, first-order logic is fixed minor tractable. And the way you do is, well, we're given the formula phi and this graph G from C. Then we can apply a structure theorem that Robertson and Seymour proved, which basically says that there is a tree decomposition of this graph. Yeah? And we can compute this tree decomposition. So it's the same as for Cosell's theorem, only these individual bags of the tree decomposition are no longer small, they're super large. I mean, they can be, in principle, they could be as large nearly as the complete graph. Yeah, so this doesn't give us much. But the second part of the structure theorem tells us that these individual bags here are structurally much simpler than the original graph. In particular, they have nearly bounded local tree width, except for a very small number of vertices. Yeah. So this is a formulation of the structure theorem that Grohe once proved. So it doesn't. The original structure theorem talks about surfaces and embeddings and APCs and so on. We don't need this. We only need the simple form here. Yeah. But if you see this, then basically, well, we know how to solve first-order model checking on such graphs, right? Because we know what you do on bounded local tree width graphs. In first-order logic, adding a constant number of extra vertices never, I mean, it's no problem. You just throw them away and replace them by colors. So we know how to do model checking on these graphs. And then by the same technique as Cosell's theorem yesterday, we know how to do model checking if you have a tree decomposition over such graphs. Right? And this is essentially all you need to do. Getting that it's technically right is a little bit more tedious somehow, but it's not super complicated. Right? Once you get the idea and understand this decomposition stuff. And so this is basically the idea how Flum and Grohe proved this result. Right? And in fact, at the last Newton Institute workshop I was here 6 years ago, we discussed whether this could be extended to a local version of it. So this is something Anush, Martin, and I did. So what we want to do is, we now consider graphs where, well, so classes of graphs that contain every graph as a minor, but locally in each neighborhood, depending on the radius, we exclude a minor. Right? It's the same as from tree width to go to local tree width. Here we can go from excluding a minor to locally in each neighborhood, we exclude a minor. And basically using the same locality-based arguments, we wanted to show that we can extend Flum-Grohe's result to these classes of graphs, which are much more general. In particular, they include a bounded local tree width, which minor closed classes don't. Right? It's a bit more work than just this. So basically, the theorem we proved was that first one, model checking on class excluding a fixed minor is also fixed parameter tractable if h is part of the parameter, right? So Flohrmann-Gauss theorem, the size of the excluded minor occurs in the degree of the polynomials you get, and in our case it doesn't anymore, right? So it's just the parameter is 5 plus h, and then there's some degree.
Not MSO then?
No, not MSO, yes. Boy, I actually copied this from somewhere. Okay, this is first alert. So always trust the headlines. Yeah? Never read the articles. Trust the headlines, and you'll be happy. Yeah. Yeah. So, sorry. This is first alert. Yeah, it would be brilliant, and in fact, also brilliantly false if that was MSO. Right. And once we prove this, this is where all the work basically goes into. So we have to compute this decomposition theorem sort of in a different way, so that we can actually get this parameterization. Then the same proof you've seen yesterday shows that first model checking is tractable on these graphs. Okay. And then that proves this result. And the last one, this is the most recent result by Dvorak, Karl, and Robin Thomas in 2010. Well, there's a story why there are so many people here, but this is the publication basically. That first model checking is fixed parameter tractable even on a much larger class of graphs, namely called bounded expansion. Maybe if I flash forward here to this one. So we are basically here, we have excluded minus and bounded local tree width. These are incomparable. What you've seen is this thing here, locally excluded minus. And now we are going one step up towards bounded expansion. Yeah. Now this I only want to sketch very briefly because there's no intuitive proof somehow. I mean, it's very technical and quantify elimination. I don't even want to define bounded expansion. I mean, this is a definition. Yeah, it's equivalent to the original definition, and maybe even understand what it says. So class C of graphs is bounded expansion if the following is true. For every number k, so your favorite number k you want to give me, there is a number n of k, so that if you give me a graph from your class, I find a proper vertex coloring by just n of k colors, yeah, like this. So this is a real, like a 3 coloring only with n of k colors. So that if I pick randomly or arbitrarily at most k color classes, then the union of these induces a subgraph of very small tree width. Yeah. Even less than this, it's tree depth, but I haven't defined tree depth, so we don't care. Right? And so basically what this means, this gives another way of covering a whole graph by small tree with subgraphs. Right? In the same way as if we used neighborhoods in growth theorem, here we cover the graph by this union of color classes. And then you can do some quantifier elimination argument. Basically, every formula is equivalent to an existential first order formula on these sort of union of color classes, and then you do some further coding, and then you get an existential formula on the whole graph that's equivalent to the original one, and then sort of this is how you do model checking. But I've really tried, and there's no good intuition more than this. Right? I mean, the rest is sort of formula coding and so on. There should be something nicer. And,
now you're saying there is quantifier elimination here?
well, it's not quantifier elimination as you know it. I mean, it's you replace you replace universal quantifiers by a whole bunch of existential quantifiers. I mean, the tree that just means these things are subgraphs of trees, basically, right? And in a tree, you can code the universal quantifier by sort of existential types, union of existential types, if you want. If you add sufficient structure to it. And this allows you to eliminate universal quantifiers within any such color class. And then you apply, so then you've converted your formula into a much larger formula that has one universal quantifier less. So you recolor the whole graph using lots of more colors. And then you apply this argument up to the point where you have no universal quantifiers left. Yeah. But it's a very subtle thing somehow. So we really try very hard to avoid this recoloring. Right? So there's this open problem, which I'll state in the very end, but now I can state it as well here. Whether first order logic is fixed parameter tractable or normal dense classes of graphs. And they are defined in exactly the same way, except this number n of k is now sort of n to the little of 1. So it's subs. Yeah, so you use a number of colors that is depending on the number of vertices, but it's smaller, right? And if you could avoid the recoloring thing here, then you would get this for normal dense. And we really tried for a long time, and In fact, this is the reason why you see so many names here, right? All of these names, except for Martin, tried to get this for normal dense. Everyone had a false proof. All proofs go through for bounded expansion, and they were the first to publish, so to speak. Right? And we still don't know what happens to normal dense. And this is sort of why it's a little tricky to get. There's more behind it than we just said in this coding. Anyway, what I wanted to talk about today is something else. I'll skip over this now. And this is basically the complete picture as we have it now. We want to get this for local bounded expansion. You can apply locality and you get this for locally bounded expansion. It's the same thing as you've seen now. And the open problem, now in fact the big open problem here is whether you can get this for lower dense. Because I'll show you later that you can't get beyond lower dense in some sense. So that will be the natural threshold for first order logic. We are making progress towards this, but like infinite inductions, if you prove one by one, then it takes infinite time. So we're not really anywhere near this at the moment. Okay, so now I wanted to come to the second part of the tutorial, which I really wanted to talk about today, where we want to prove corresponding lower bounds. So all what we've seen so far is I give you a class of graphs and they show FO is tractable or MSO is tractable. Of course, the natural counterpart is to say, look, Cosell proved that MSO2 is tractable on bounded tree-width graphs classes. So the question is, can we go beyond, right? I mean, it would be very nice if Cosell's theorem could be extended beyond classes that have a constant bound in the tree-width. And somewhat surprisingly, this has not been studied so much. And only very recently there were sort of stricter lower bounds. And in the rest of the next sort of 40 minutes or so, depending on the call, I want to prove one of these lower bounds very sort of in some depth at least, so they can see the techniques we can use to prove such bounds. Right? So it's going to be a little more, less service time, a little more sort of proof in the remaining half an hour. Right? So what I want to, so here's again the reminder of Cosell's theorem. If C is a class of graphs that has a constant bound on the tree width, then MSO2 model checking, and for once the slide is correct, is fixed parameter tractable on the class C. And in fact it goes by linear time arithmetic. Okay. And now we want to basically, the question is, can we go beyond? So other classes of unbounded tree width for which we also get model checking for MSO2, and what are these classes like? So what I wanted to show, would like to show, but it's false unfortunately, is that if C is a class of graphs that has unbounded tree width, then MSO2 model checking is not FPT on that class. Yeah? But this is wrong, yeah? Sadly or not sadly, depending on your point of view, obviously. So Markowski and Marinho, they gave a class of graphs already in 2004, which is unbounded tree width, and MSO2 model checking is still tractable on that class. Yeah? It's not super surprising that this exists, but they exhibit these examples, right? Sorry?
Is C2 in a class called cliques? Isn't that right?
No. Cliques MSO2. On cliques you're lost, right?
Sorry?
If you have cliques and MSO2, then that's too much, right? And there's a proof that MSO2 model checking is not FPT on cliques.
No, if it's just cliques, it's fine. I mean, you're going to close it under subgraphs after that.
No, even on cliques. There is Markowski and who else is it? They gave an argument unless, surprisingly, unless x time is the same as nx time, MSO2 is not doable on cliques, right? So it's basically a monadic encoding of sort of Turing machine stuff. I've forgotten who the second author is. It's 2005 or so. May even be in this paper, but I don't think so. Do you know where it is? Okay. I say, yeah, but it's a good point. So this is important. We are talking here about MSO2, so quantification of a set of edges is allowed. For MSO1, this is there are much larger classes of unbounded tree width where this is tractable, right? And so this, and you'll see later exactly where we need quantification of a set of edges. Yeah. Right. So in this strictness, we can't prove this result because we have examples of graph class of unbounded tree width where MSO2 is tractable. But we can prove something similar. So we can show that if the tree width is too unbounded, let's say, then MSO2 model checking is no longer FPT. And to make this precise, obviously we need to classify what we mean by really too unbounded tree width of a class of graphs. Yeah? And so basically what we want to allow is the tree width can be unbounded, but we measure how large the tree width is in terms of the size of the graphs you will find in the class. Yeah? And so if f is any function, then we say that C, a class C of graphs has f-bounded tree width if the tree width of any member of this class is at most f of its order, where this is the order of a graph is the number of vertices. Yeah? And so in Coselle's theorem, f of n is just a constant because we have a constant upper bound on the tree width of any member of C. The largest function that makes sense is linear, right? Because every graph is a tree width that knows its number of vertices. And what we want to study is classes of graphs where the tree width is roughly at most logarithmic in the size of the graph, the order of the graph. Yeah? And for such classes here with this bound, we can show intractability results. And so, more precisely, the theorem that Markowski and Marigny proved is that there are classes of graphs of roughly, logarithmic tree width, basically. So the tree width goes logarithmic with the size of the graph, but not more than this, on which MSO2 is tractable. Right? And so by this, obviously, lower bounds we can't prove below the logarithmic tree width. Right? And this is the sort of the best we can hope for. And so what we want to show is, and what we will show actually, is that nearly if the tree width of C is not bounded logarithmically, so log to the C for some small constant C, which currently is something like 28 or so, then MSO2 model checking and is not FPT on C. Yeah. And I'll probably keep on forgetting the 2, but everything I say now is has a MSO2. Yeah. Okay. The problem with this is, and I mentioned this yesterday already, some monadic second order logic is model checking is in polynomial space. So if you were able to prove any real lower bound that MSO is not FPT on a class of graphs, then we would separate P time from polynomial space, which would be nice, but not what we aim for here. So all of these things have to be subject to complexity theoretical assumptions. And this is not only that the theorem will have a complexity theoretical assumption, it also means the only way we know how to show lower bounds for MSO2 in a class C of graphs is to use reduction from sort of an NP-hard or a hard problem to model checking. Yeah? And maybe just a quick, the group photo is still on after the talk, even though I'm erasing this. So essentially what we will be doing, for lack of alternatives, as it were, is the following. So take satisfiability. So the proposition satisfiability problem, and we want to know whether a formula, I'll call it W for now, is a satisfiable instance. Then what we do is we will construct a graph in C and a formula phi in MSO2 so that G models phi if and only if W is in set. Yeah, I mean, that's not a very surprising idea, obviously. And so what we have to do for this is somehow we will have to encode the SUT instance W somewhere in the graph, right? So we'll find somewhere something in the graph in which we can encode this instance, right? And this general technique, obviously, it requires us to know a little bit more about C and the graphs, how they look like, than just knowing that the tree width is high. And this is so we will prove this lower bound here up to some further technical conditions. And this is what comes next. So let f again be the function, the tree width bound, as it were, logarithmic. And p is a polynomial. Then we say the tree width of a class C of graphs is fp unbounded if the following is true. So first of all, there is a number at most, well, less than 1, so epsilon less than 1, well, and bigger than 0, obviously. But, yeah. So that for all large enough, no, actually for all n, but large enough is enough. The class C contains a graph Gn whose tree width is somewhere between n and p of n. And this is the graph Gn is a witness that the class C has not bounded tree width, right? So its tree width must be at least f of g of n. Yeah? And then furthermore, given n in unary, we can construct this graph in time, in sub-exponential time. Yeah? And then we call the tree width of C f unbounded if it's fp unbounded for some polynomial. So what does it mean? Essentially, okay, let C be the class of graphs we are working in. Yeah, so that's your class. well, we know it has unbounded tree width, but it's not good enough if there's only very few examples of graphs that have very large tree width, right? Because we want to be able to reduce a set instance into this and say if we only had witnesses that the tree width is very large, so that the tree width is at least logarithmic for very, very few values of n, so growing, say, double exponential in n or something, then there just wouldn't be enough graphs to reduce sufficiently many w's to, right? And this is the first condition we have here, that we have for every n sort of the gaps between witnesses of high tree width are not too large, are just polynomial, right? That's the first condition basically. And the second one is, of course, if you want to reduce sort of w into a graph in your class, then we must be able to compute such a witness, right? If you don't know how to compute them, there's no reduction you can apply. And this is the second condition. And the numbers you can just ignore, they are just so that it works, if you like. Yeah. But you'll see exactly where this is needed in a few moments. Okay. And then the theorem I want to show you now how it works is that if C is a class of graphs which is closed under subgraphs, and there is such a polynomial of degree at most gamma, then if the tree width is not log to the 28 plus gamma bounded, then MSO2 model checking is not FPT. Yeah? And the complexity theoretical assumption is unless satisfiability can be solved in a sub-exponential time. And this is something, yeah, it's obviously much weaker than P versus NP, but it's widely believed that this is not possible. Right? And the parameter here is just the size of the formula. Right? In fact, we will prove a much stronger result. It's not even in the complexity class XP, but yeah, that's not so relevant. Yeah. All right. So how is it proved?
Stephan?
Yeah.
By this assumption, do you mean the exponential time hypothesis or something like that?
No, exponential, uniform exponential time hypothesis. Yeah, I just don't want to define it, which is essentially this thing somehow. Yeah, yeah, exactly. And it's a uniform version, so there's also variants of this theorem that have come up this year, something where there's non-uniform, but this is the uniform version. Yeah. All right, so how is it proved? Well, the proof idea is just exactly what I put here on the blackboard. So we will reduce the propositional satisfiability problem to model checking for MSO2 on this class of graphs. So given such a formula, the first thing is we construct a graph in C whose tree width is, well, it's actually quadratic in the size of the formula, and you'll see why in a moment, and which is a witness that the tree width is not logarithmically bounded. Yeah? And the first two conditions just say such a graph exists, and we can compute it in sub-exponential time. Yeah? In the size of it. Yeah? And then this is the tricky part. We will encode this formula W in the subgraph. Yeah? So somehow we will push this into the graph, and this is the most important thing. And here we use the closure on the subgraph so that whatever we encode it into will actually exist in our class C. And then we'll define a formula phi that's independent of the input, which is true in the graph if and only if W is satisfiable. Yeah, but this obviously must not depend on W, and it won't. And then if this was fixed parameter tractable, or if this was doable in XP, then we could decide whether W is satisfiable in polynomial time. Okay. So that's the plan. But maybe, and this is the outline of the proof. So we will first see sort of some very simple intractability results. Right? And most of you, so the fundamental theory fraction in the audience will certainly know how it works. Yeah, so this is really not too difficult. And then step by step we'll get to the full result. And so of grids and walls. So the first intractability result I want to show is that MSO2 is not FPT on the class of grids, or colored grids as it were. And a colored grid is just this thing. So it's a graph that looks like this. We have 4 rows and then 5 columns, and they are connected as you see it here. Right? So this is just a special case of a 4x5 grid, and obviously we generalize to any size. And a colored grid is just a grid where the vertices can be colored by 2 colors, red and blue. Right? And the simplest result you can possibly prove is that if G is just a class of such colored grids, then MSO model checking is not FPT on it unless P is the same as NP. Yeah? And here's how it goes. So again, it's by a reduction of propositional satisfiability. which clearly is NP-complete, and it can be solved in quadratic time by a non-deterministic Turing machine. And basically, we will just simulate the run of such a Turing machine deciding the set problem in the grid. So given your set instance W, what we do is, well, you just look at the time-space diagram of an accepting run of M on W if the formula is satisfiable, which will look like this. Yeah, it can be of size at most quadratic, but here we have the input configuration, so the formula and some blanks, and then this is just the run of the Turing machine with the read head moving across. Yeah. And so now this, basically we want to guess the space diagram on the vertices of the grid. And that's why we take grids, because this is what you can just guess. Right, so the proof goes as follows. You give me your set instance, I construct an n square by n square grid, which is big enough to contain the whole space-time diagram. And I color its bottom row by the inputs, where red stands for 0 and blue stands for 1, and black is just empty space. Yeah. And now I construct an MSO formula, which you see here, basically, that just guesses the coloring that corresponds to the space-time diagram of a successful run of the Turing machine. So we just have a bunch of existential quantifiers. So x0 just guesses the position where in the diagram there will be a 0, x1 guesses the ones, blanks guesses the blank symbols. And then for every possible state of the Turing machine, we guess a relation that contains the vertices where the state is the machine is in state Q. And then we have a first order kernel, basically, and all this kernel has to say is, we put a 1 here only if this is a valid transition of the Turing machine, but then of course whether there's a 1 on some symbol only depends on the 3 symbols below it in the Turing machine, right? By definition. And so the first order formula, this is very easy, encoded in first order logic, and just guess the time-space diagram, and then decide whether at the end you have an accepting state.
Do you need some sort of orientation?
Yeah, you need some orientation, which I'm skipping over here. So the orientation you get by coloring, making sure that the top left, no, the bottom left corner is colored and the others aren't, basically. Yeah. And then whether that's up or down, I mean, it's an n by n square by n square grid, so it doesn't really matter. Yeah. But it's a good point. I mean, you need somehow to fix what the bottom row is, but this you get by the coloring. Yeah. If you don't get it by the coloring, then you hard code it into it. In fact, we'll see this on the next slide. Yeah, so this is basically the proof that on the class of color grids, MSO1 model checking is not FBT even. And in fact, it's not even in XP if you compute it correctly. Yeah. So color grids are, of course, I mean, yeah, exactly what you need for time-space diagram sort of solution. So as I said, that's the easiest case. Or let me complete the argument. Right, so with this reduction, of course, if you now could check whether the formula phi m is constructed is true in the graph GW in XP time, so the size of the grid raised to something depending on the formula, then it means this formula is true in the graph can be decided in this time here, but phi m is just a fixed formula. So basically, we can decide whether the set formula is satisfiable in polynomial time. Yeah. All right. So as I said, colors are, of course, very strong. So the next result you can prove is you can get rid of the colors. So basically, instead of using colors to color the vertices by the input formula, we can just delete adjacent edges. Right? So if you want to color a vertex red, then you delete the adjacent edge. And if you want to color it blue, then you keep this edge on the bottom row. And then it's very trivial exercise to rewrite the MSO formula to decode this encoding here and then do the same thing as before. And here, because you're deleting edges, you really somehow have to make sure that you're giving it an orientation. So we always delete the leftmost edge on the bottom row and always keep the last one. Yeah? Then you know what's left and right, and then you can decode everything as it were. Okay, so grids are bad, basically. Subclass of grids are bad for MSO model checking, and this will be at the heart of our result. But why are grids interesting in the first place, except that they are hard for model checking? And this is based on a theorem by Robinson and Seamer, who proved that if a graph has high tree width, then it contains a large grid. Yeah? So the theorem, which is known as the excluded grid theorem, says that there is a computable function f from n to n, so that for every graph G, if the tree width of G is at most f of k for some value of k, then G contains a k by k grid as a minor. And an immediate consequence you get from this is a theorem by Markovsky and Marigno. If C happens to be a class of graphs of unbounded tree width, but that's minor closed, yeah? So whenever you have a minor of a graph in C, then that minor is also in C. Then you immediately get that MSO2 is not fixed point retractable on that class unless P equals NP. Right? Because then you have the class of all subgraphs of grid in your class itself, and then the same intractability result goes through. Yeah? But this is an extremely strong, okay, no, I'll take this back. This is a very strong assumption, right? I mean, unbounded tree width and minor close is very strong classes of graphs. Right? And it can strengthen it slightly to topological minus if you know what this is, and you use walls instead of grids. It's the same proof, same idea, everything goes through. Right, so these type of classes you get intractability for free, basically. Okay, so now let's come back to the main theorem we wanted to prove. Yeah, namely, if C is any class, it's closed in a subgraph, but not closed in a taking minus. Yeah, and that's important here. And its tree width is basically not logarithmically bounded. Yeah. Then we want to show that by the same argument, MSO2 monochecking is not FBT. Yeah, this is just what FP unboundedness means. Okay. So here's a first idea that looks very good, but it's equally wrong. Namely, to use the excluded grid theorem, right? Which is just a repetition of the theorem. So the idea would just be, well, you give me your propositional logic formula you want to decide satisfiability. I construct a graph in my class GW so that it does contain the W square by W square grid, yeah, as a minor, but minus, we can define minus in MSO2. And we proceed as before, because these graphs we know as the tree width is very high of our class. Right? The only problem is the currently best bound known for the excluded grid theorem is exponential in the size. Right? So if you want to find an n square by n square grid, then your graph must have exponential tree with an n. Right? So the grid we would like to find where we encode Wn is actually a lot smaller than we would like it to. It's only logarithmic in n. And if you then recall that we are working in classes of graphs where the tree width is only logarithmic in the size of the graphs, then this grid is really, really tiny. Yeah? And so if you simulate any run of a Turing machine on that super tiny grid, which probably you can't even read in the back, it essentially means you have a sub-double exponential time simulation of an NP Turing machine, but in sub-double exponential time you can simulate anything. Right? So there's nothing you can really gain in terms of lower bounds. Right? So this is too tiny, actually, and the problem really here is that the grid theorem, we don't know any polynomial bound. Yeah? So we could easily cut 30 pages out of our proof if we had a polynomial bound here. And everyone. Yeah, so it's,
wouldn't then the construction of Marigno and Markovsky show that this bound cannot be proved?
No. Markovsky and Marigno really have logarithmic, and we have just a bit over logarithmic. Yeah? I mean, if you could prove the exclude grid theorem, say the tree width has to be n to the 17 or so to get an n by n grid, then the 28 we have in the theorem here would sort of be 17 times 2 times plus a bit. Yeah? So if you can prove the degree of the polynomial you can prove for the grid theorem would give this, goes into this 28 here, basically. But hang on a second, I'll prove a grid theorem and then you'll see how this depends on the polynomial size. Yeah? Okay, so and this is the main problem, and therefore we have to do something else. We can't prove an excluded grid theorem with polynomial size. That would be brilliant, but we don't know how to do it. So we just do something else. And what we do is we replace grids by something that's grid-like, and for which we have a polynomial excluded grid theorem. And this is something that Reed and Wood introduced a few years ago, 2008. And they proved if the graph G has tree width at least k to the 5, then it contains two sets of pairwise disjoint paths, so P and Q. So we have a couple of red paths, which are pairwise vertex disjoint. And we have a couple of blue paths, right, intersecting them a lot. And then that looks like a grid, only the intersection can be very badly. Yeah? I mean, so there's no, we don't really know how the blue ones and the red one intersect. Yeah? Well, what they proved is we can find two sets P and Q like this so that their intersection graph contains a clique minor. Yeah? The intersection graph is the following thing. It's a graph that has every vertex as vertices. We have the path in P and the path in Q. Yeah? So the red one and the blue one. And we draw an edge between a red path and a blue path if they share a vertex. Yeah? And that gives you the intersection graph. And we can then always find P and Q so that this contains a KK minor. Yeah? And the dependence on K is just polynomial, it's K to the 5. Yeah? And essentially what we, instead of grids, we want to use such pairs of the intersection graph basically as a replacement structure for grids. Yeah? So the first problem we had to solve, I mean, this proof is not really constructive, so we made it constructive. That's the first theorem here. There is a constant C so that, and a polynomial time algorithm, so that if the graph G has tree with at least K times C times K to the 12, then we can compute a topological grid-like minor of order K in the graph. Yeah? So the bounds are a little bit from 5 we go to 12, but instead we can actually compute this. If you believe in randomized algorithms, then we can match the best bounds. So there's a randomized algorithm that finds the things we want to find, and the dependence is only L to the 5. Okay. But randomized is not good enough for us. Yeah.
Why do you move to topological grid-like minor?
Because we can.
What is the relationship between intersection graph having a KK?
Well, that's a generic ratio. If the average degree of the intersection graph is high enough, then you will also find a topological clique. And I mean, topological grid-like minors, topological cliques are a lot easier to work with in MSO. But we do everything in terms of grid-like minors, so real proper minors, so it doesn't really matter. Yeah, this is just because it works and it doesn't matter, so ignore this for a moment. Yeah. Okay, so basically what this says is this theorem here is effective. We can compute the objects we want to compute in polynomial time. All right, so now this is the second good idea, which is also wrong, but not as wrong as the first one. So we do the same trick as we've done all the time now, but we use grid-like minors instead of grids as objects. Right? So again, you give me your favorite propositional logic formula, and I want to decide whether it's satisfiable. So what I do is I just compute a graph GW in my class C, whose tree width is at least W, the length of W to the 28. I mean, ignore all numbers here. It just works out in the end. So it's polynomial in W. Right, then by the theorem we've just proved is we can then compute two sets of pairwise disjoint paths, P and Q, that gives us a grid-like minor in it. Yeah, this thing then, the intersection graph of these paths induces a large clique, yeah, so that's good. And since we're working in MSO2, this clique obviously contains a large grid, yeah, and then in this grid we can do whatever we've done before, right? So the idea would now be we encode the input W by deleting edges in the bottom row of this grid, which we find as a subgraph of the clique, which we find as the intersection graph here. Yeah?
How do you find the grid in the clique, and how do you get the ordering on the grid?
Yeah, you could in principle, but it's not working anyway, so I'll show you how you No, but it's not working on a very surprising thing. This we could all do somehow. Yeah? Essentially, this is definable, and I'll show you. No, I won't show you the MSO formula, but there is an MSO formula that defines the P and Q, and then there's an interpretation that would define your clique. Because you're working in MSO2, you would just guess the subgrid in your clique. Yeah? I mean, MSO2 allows you to guess sets of edges, yeah, and in a clique just means you have every edge, right? So you just guess a grid, yeah, and then. The problem is this part here, right? Because, well, what it means here is every vertex in this intersection graph corresponds to a path, right? And every edge here corresponds to the intersection of two paths, right? So if you want to delete an edge in the intersection graph, what it really means is we're deleting the intersection between two paths. So we're deleting a vertex in G. Yeah? But if you start deleting a vertex in G, then you're completing breaking up this grid-like minor, right? Because then the path, if you delete a vertex in the middle, you have two paths, right? And there's no way how you would actually connect them. And so this is really the obstacle we don't know how to solve. That deleting edges in the intersection graph means deleting vertices, and this is not what we don't know how to do it. Yeah? And so the problem is really encoding W into this intersection graph. Everything else we could probably solve. So yeah, so we have to do it differently. And let me give you first some, hopefully, some intuition how we do it. Yeah, sorry. Yeah, good. So the last 25 or so minutes. This is how it works. Yeah, so we have this graph G, yeah, and as you see, it has to be fairly large. And in this graph, what we find is this grid-like minor. So it works exactly as this, right? So we have the red path somewhere here, and then we have the blue stuff. Yeah, that we don't know actually what it looks like. Yeah. And the problem is, how do we actually encode this W inside this grid-like minor? And so what we do is we will add something in the rest of the graph, yeah, namely a tree. We will encode W in this tree and then sort of connect the grid-like minor nicely to this tree, so that we can basically, the encoding of W in here can then be transferred to the encoding of W in the grid-like minor. That's the basic idea. Yeah? So what we can show is, you can not only find the grid-like minor, you can also find a large tree whose leaves basically are the endpoints of the red path. Yeah? And so those of you who know the excluded grid theorem and Diesel's way of proving it, this is exactly the mesh kind of thing that you would compute. So this is not very complicated to get. Yeah? So this is good because it means everything we encode in the tree naturally sort of translates into encoding of the red path, and then this is all fine. The first thing we have to do is we have to define an ordering on this tree. Yeah? So that we get an ordering on the red path and then an ordering on the grid-like minor. And this we just do by throwing away half of the tree, or in fact a bit more, but not too much. So whenever you have a situation like this in the tree, then we will delete the subtree, yeah? So that vertex only has a leaf as a neighbor. No, actually this is wrong. If you have a situation like this, yeah, then we will throw this away. Yeah? And so then at this vertex here, we have one neighbor that has a leaf as a neighbor, and this one doesn't. And so that's left, that's right. Yeah? And then if you do it carefully enough, you end up with a tree that looks exactly like this. Yeah? So it has an ordering imposed by this definition, and it's still big enough. Right? So you lose a polynomial factor, but there we go. So once we are doing this, we now have a tree that has an ordering on it. Yeah, okay. So the next thing is we want to encode the word W in it. And again, we do so by deleting some part of the tree. Yeah? So essentially what we do is here at the end, we make sure that the tree looks like this, yeah, or it looks like this. Wait, is it big enough? Can you actually read this? Yeah. Let me draw it a little bit bigger. So we call this thing here a cross, and this thing here a double cross. Yeah? And if the tree is big enough, then the sort of close to the leaves, we can delete sufficient subtrees so that we get one of these two informations, and that will encode a 1, and that will encode a 0, or the other way around. Yeah? And so this is how we basically encode the W. According to this ordering, we delete a few more vertices to get one of the two situations. And not exactly, we use a slightly different form here, but this is what you get. And then what you're left with is basically a tree that looks like this. Yeah? So some leaves are connected to the red path. In between any two of them, you either have a cross or a double cross. And then that gives us the word W, and it gives us an ordering on W, and this gives us an ordering on the red vertex, on the red path, and then this is all we want. Yeah? And this is a little bit tricky to get somehow, but you can do this. Yeah? So it's just a bit of combinatorics to get this all done. And so we call these things label tree ordered webs encoding W. And this is exactly what you see here, right? So it's a tree on which there's an MSO definable ordering. Then there are these things hanging off it, so crosses or double crosses, and then the rest of the grid-like minor is attached to it nicely. And there's a polynomial time algorithm that, given a word of length L, and D is the constant, this is the sort of degree of the running time of the Turing machine, we can compute this thing. So we can compute a graph G of tree width bounded by this one here, which contains this labeled tree ordered web as a subgraph. And this is nearly everything we need. So what's the last problems why are doing all this stuff? I mean, if you look at this, of course, well, I've used 3 colors, right? So you have the blue one and the red one, which is the grid-like minor, and then the tree is sort of like black. So that makes it easy to define an MSO. In reality, of course, there are no colors in your graph, right? So the grid-like minor, the tree and the grid-like minor and everything, this is all just black if you want, right? So the main problem is, how do you actually distinguish an MSO between a tree and this crosses and the stuff in the grid-like minor? Because everything you find here could also, in principle, be present in the minor. And this is the most complicated part. So this tree is defined in a way that's uniquely definable in monetic second-order logic. So we know what the tree is by a formula. Then this ordering defined on tree is also MSO decodable. This is easy to see if you follow this construction. The crosses and double crosses are also extremely easy to, in first-order logic, to define. So we know which leaves here are labeled by 0 and by 1. And then we use an MSO formula that decodes this grid-like minor and defines a wall in it, which is ordered in this way, right? And then we are done. And this can all be done. It's a little bit, it's a bit tedious to work and takes a while, but then you get this formula. And then we are done, basically. So this thing you've seen now, it's the same proof as before. This is the main result here again. So if C is a class of graphs closed in a subgraphs, which is not locked to the 28 bounded tree width, then we can do what we wanted to do. You give me your favorite satisfiability proposition logic formula. Then I construct the graph G in my class that contains such a tree labeled web encoding this formula. This can be done in sub-exponential time by the conditions we have. And then if that graph satisfies the formula phi, then you know your propositional formula is satisfiable. And hence, if you could do this in xp time, so this size here, then if you do it right, it would mean we can do this in sub-exponential time, decide whether W is satisfiable. And this is, as you see, there are not too many slides left. So what you see here is obviously there's a gap. So the tree width we relate to is log to the 28. Cousell's theorem just says if the tree width of C is bounded by fixed constants, then MSO is tractable. So there's an obvious gap between constant tree width where it's tractable and logarithmic tree width where it's not. But as I said before, it's impossible really to close this gap because Markowski and Mourinho give this example of logarithmic tree width where we have tractable model checking. And you can also construct sort of examples of logarithmic tree width where it's unlikely to be tractable somehow. So it would appear that between constant tree width and logarithmic tree width there's sort of a gray area where you have some classes where it's tractable and some where it's not. So the real gap is between logarithmic tree width and log 28, and that's open. And personally, I'm not. I guess if you put in a sufficient effort, you could bring this down to something better than 28, but we certainly won't touch this again. It's now, it's been a lot of pain getting it. So no, it's not. Right, so to conclude, so this is now the slide you've seen, basically. Again, I had a night to switch the numbers, but it's the same slide, obviously. So what we've kind of proved up to this logarithmic gap is that much beyond bounded tree with MSO1 model checking cannot be extended. Right? So it's tractable there, but it's not much beyond. It would be nice to have this for MSO1 on bounded click width. So in principle, the same kind of proof could work, except we have there are no grid-like minors for bounded click width. So there's really nothing in obstruction. The best obstruction is again logarithmic in the click width, and that's not good enough. Besides the obstruction being terrible, So there we don't really know what to do. This is a good question, but we need more graph theory.
Is bounded click width closed under complement? I mean, graph complement, I mean. Because MSO1, I mean, if model checking on a class is for MSO1,
you would need the condition that the class has unbounded click width and it's closed in an induced subgraph. Yeah. So that the complement trick wouldn't work.
the complement.
Yeah, this is an excellent remark. So what's easy to see is if any logic, like first order logic, is FPT on the class of graphs, then it's also FPT on the class of complement graphs, right? Just in the formula, whenever you say there is an edge between x and y, then you say there's no edge between x and y. It's the same thing. Right? And so that's the other reason why we need closure on the subgraphs to sort of prevent this complement clicks. I mean, there's a whole more to be done on this, right? So I mean, basically, any first order interpretation would, retain tractability and so on, then you get lost. Anyway, because Nicole's getting nervous, I just want the last one slide. There's also, as I said, a very, very easy lower bound for first order logic. So we've seen this result here that first order model checking is FPT on any class of locally bounded expansion. And it's not very difficult to see under some technical conditions that look a little bit like the one you've seen for MSO. If C is nowhere dense, is not nowhere dense and it's closed in the subgraphs, then first order model checking is not FPT on that class. Unless P equals NP, and that's a very simple proof. Okay. So if you come back to this picture here, basically you can't go beyond nowhere dense if you're closed in the subgraphs. We are nearly there, but there's this gap, and I think that's the main open problem here at the moment. Yeah, so to conclude, this slide you've seen before. This is the research program this tutorial was about, to provide upper and lower bounds and give characterizations for tractability for logic in terms of graph structural properties. And you've seen there are a few results and some nearly nice characterizations. The main open problems really is nowhere denseness, tractability of first order logic, and lower bounds for monadic second order logic on graphs of small click width. And I would expect that there is such a thing. I don't conjecture. I conjecture that you can't, with MSO1, you can't go much beyond click width if you want. Yeah. So there should be, in principle, something similar to this stuff working on MSO1 and bounded click width. It's just we don't have the tools at the moment. But I think that's a real challenge here to do something about it. Well, thank you very much.
So what's, you mentioned that MSO1 is doable in bounded click width, but a few years ago we didn't know how to find the click decomposition. Do we know by now?
Yes, we know how to find a rank decomposition, and from a rank decomposition you can find a click decomposition. The gap is exponential, so you can find a rank decomposition, optimal rank decomposition in time n to the 5 or so, FPT time. This is Sangil and Peter Yenny and this kind of stuff. And from a rank decomposition, you can find a click decomposition of exponential width somehow. This I've forgotten. I think it's Sangil as well who shows how this is doable. So you can make them effective, but I mean the gap is.
Do any of the low bounds for MSO distinguish between XP and FPT, or do they all work equally well for XP?
Not at the moment. So basically, tractability is in FPT, and intractability we have is not in XP. Yeah, so it's.
So I guess the question is to weaken the complexity assumption and get a.
No, I don't think that will. I don't think that will work really, because the formula somehow. I mean, yeah, possibly, okay, but as long as you use reductions in this sense, you will always end up with something that's being encoded in the graph, and then there's a fixed formula deciding whether that's true or not. And then it doesn't really matter whether the formula is in the exponent or not. It doesn't really matter. Maybe if you had really, really different tools available to avoid the reduction stuff, then you could distinguish between FPT and XP. But I don't know. But you're right, it's somewhat surprising that there's a kind of dichotomy, right? The tractability is really in FPT and intractability is beyond XP. If there's something more to it, I don't know.
Further questions?
I was just going to say, the gap which you showed and where you said around logarithmic there are classes with logarithmic tree width where you'll have tractability and you'll have intractability. But that's only looking at only one way of classifying them, looking at tree width as a function of the size of the graph. I mean, can you think of any other measures which might, give a classification which will work?
No, good point. It's not. No, we didn't think about this much because we really wanted to show the most general only in terms of tree width, because Coselle's theorem is only working on terms of tree width. Probably.
So another to answer that question, you can think of counting the number of strongly connected components in a graph, and that can have a real effect on. For example, if you think of a SAT formula as a graph, and if it has strongly connected components, too many of them, or the entire graph is a huge strongly connected component, the SAT solver will have a difficult time solving that. On the other hand, if you have lots of individual strongly connected components that are weakly connected among each other, and you can split the graph, split the formula into smaller graphs. So
this is true. This is absolutely true. So in all these intractability results, we can only focus on graphs which are strong connected. Because I mean, the Pfeffer and Wald stuff we've seen, if there's a weak connection or small separation between parts of the graph, you cut that in two and then you solve it on the two subgraphs. So if there's intractability, it must be within some highly connected subgraph.
So the number of such highly connected components can be a parameter as well.
Yeah, it could. That's true. I mean, there could be lots of parameters you would look at. So it's likely that there exist things like that would cut through the classes of graphs of logarithmic tree with or sublogarithmic tree with, and then you could classify it. It's not. So it's not entirely clear what these parameters would look like, and the other thing is, of course, they would have to be natural enough to be interesting. But yeah,
have you spoken with any guys who actually build these model checking tools? How they could leverage these ideas? For example, you could have a model checker that what it does, it reads in a graph, for example, and it would then first try to compute this parameter, and then go ahead and call the corresponding good model checking algorithm for that.
Well, the short answer to this, no, I haven't actually spoken to model checking people, not about these kind of things. But it is true, I mean, there is work that if the tree is small, for instance, of your transition system, then you get, in principle, better algorithms. One catch of this, one problem is that computing the tree decomposition is, well, it's linear time for any k, but it's practically not so easy. And the linear time algorithms are horribly complicated. And the quadratic time algorithms that compute nice tree decompositions of approximately with only two. Well, quadratic times, if the transition system is really huge, it's not exactly what you want. I guess there's more into it, and yeah. I guess with more research, you could actually maybe use some ideas of sort of decompositions and transition systems and so on to speed up something. But I haven't looked at this.
Okay, and I think during lunchtime there is plenty of time to go on discussing things. So thank you very much to all of this morning's speakers again.